So welcome to the second part of session 2 basically. So were there any questions in the first part? Not yet? You had any question? Yes? Pulse, yeah, so you take a pulse train and you first multiply it with a complex sinusoid, which is e to the power j times 2 pi nu t. So now that means that you have shifted the pulson in frequency by nu, right? And then you delay it by tau. So those are the type of carrier waveforms basically. Okay, I'll show that in math very soon. Yeah. So we'll talk about pulsons and the basis of all pulsons. So it turns out that any time domain signal, just like in Fourier transform, what is Fourier transform? What is inverse Fourier transform? Inverse Fourier transform basically says that any time domain signal can be written as a linear combination of sinusoids. Similarly here, any time domain signal can be written as a linear combination of pulsons. You have to think of it like that. Okay, that's the basis of pulsons. Okay, it's a basis, signal basis. Okay, and when you project, see what is the Fourier transform? You have the sinusoids e to the j 2 pi ft, f is the frequency, and when you consider all possible f, you get infinitely many sinusoids of different frequencies, and that forms a basis, right? And when you take any time domain signal xt and you project it onto this basis, that's your Fourier transform, right? Similarly, when you take your time domain signal and project it onto the basis of pulsons, that's the Zach transform. Okay, it's like that. Okay, so we'll discuss the properties. We'll talk about twisted convolution in more detail, and I'll finally conclude with what's the input-output relation. So when you transmit a pulson through a doubly spread channel, what is the output? Okay, how is the output and input related? Okay, for example, I mean if you send a sinusoid through a delay-only channel, when you have an LTI channel and you just transmit a sinusoid of some frequency f, then what you receive is a sinusoid of the same frequency f, right, multiplied with a complex number which is the gain of the channel on that frequency, right, h of f, and that h of f is nothing but the Fourier transform of the impulse response evaluated at that f, right. So that's the input-output relation, right, when you work with sinusoids. But what happens when you have pulsons and you have a doubly spread channel? How are the input and output related? So we'll see all these basics. I mean this is like building up to Zach OTFS modulation. I mean these are the building blocks that we need to know, right. Okay, so this is my standard pulse train. Okay, this is just a normalizing factor. Okay, but it's basically this, right. I mean delta is a Dirac delta in time. All of you know what a Dirac delta is, and this k is going from minus infinity to plus infinity. When I say k belonging to integers, means this is a summation where k goes from minus infinity to plus infinity, and this is your pulse train, right. You all have seen this equation. When you take the Fourier transform of this pulse train, then you get this thing, right, and this is also like a pulse train but in the frequency domain, where the pulses are located at integer multiples of 1 over tau p, which I am calling as nu p. Okay. Subsequently, I will call tau p as my delay period, and I will call my nu p as my Doppler period. Okay. And they both together define the Zach transform. For different tau p nu p, you get a different Zach transform, because for a different tau p nu p, this basis is different. That's why. Now if you take your standard this pulse train and you first shift it in Doppler, so you multiply, you can try it writing in your notebook, you multiply it with e to the j 2 pi nu t, okay, and then you delay that by tau. When you do that, this is what you will get. Okay? This is what you will get. You see the pulses are shifted by tau, and you get this term which is basically your Doppler shift, right. And these kind of, this is a pulson, this is your pulson, okay. But I will call it pulson at tau nu. For different values of tau nu, you will get different pulsons, right, and there are infinitely many of them, right. And that ensemble of all possible pulsons corresponding to different pairs tau nu is what I am going to call as the basis of pulsons. That is the basis of pulsons, okay. And it turns out, and I am not doing a lot of math here, okay, but it turns out that it forms a basis. What I mean is that any time domain signal can be written as a linear combination of these pulsons. This is what I was telling, that you know the sinusoidal basis, right, and when you project any time domain signal onto this sinusoidal basis, you get the frequency domain representation of that same signal, which you call as the Fourier transform, right. Fourier transform is nothing but the frequency domain representation of the same signal. The signal is the same, you are just looking it through a different lens, okay. It has time domain representation, it also has frequency domain representation, but it is basically the same signal, right. I define a third representation. You already know time and frequency. I define this third representation called the delay-Doppler representation, and the way to get the delay-Doppler is you simply again project xt onto the basis of pulsons. So, you do this integration, you take xt, I mean this is the projection operation, right. So, when you project xt onto the pulson tau comma nu, you have to do this integration, and for that you can, I mean it is very easy integration, you just take the expression of p tau nu from the previous slide and you just put it here. Anybody who has done signal and systems can do that integration in 1 second, okay. And when you do that, you will get this thing, okay. So, this is the Zach transform, okay. This is the Zach transform. So, given a signal x of t, this is the delay-Doppler representation of the same signal, okay. Or is it, I think conceptually is the same thing, right. It turns out that the DD domain realization or representation of any signal is a quasi-periodic function in the delay-Doppler domain. What I mean to say is that if you shift tau and nu by integer multiples of the delay and the Doppler period, okay, where n and m are arbitrary integers, then it is exactly equal to x dd tau nu, but you get this term here, okay. Actually, if n is equal to 0, then you will not get, then it will be exact equality, right, which means that if you shift, if you go along the Doppler domain, then the signal is periodic, the delay Doppler representation is periodic along the Doppler domain with a period of nu p. But along the delay domain you have this factor coming in, okay. That is why I have to use this word quasi, that is why this quasi is used here, okay. And then because it forms a basis, you can write any time domain signal as a sum of these different pulsons, and but you have to weigh them with this, right. I mean it is just like your inverse Fourier transform. In the inverse Fourier transform, instead of this you have e to the j 2 pi f t, that is the waveform, that is the basis waveform, and you multiply it with what? E to the j 2 pi f t is at frequency f, so you multiply with x f and you just integrate all of them, you add all of them, df. It is the same thing, exactly same thing. So, this is called the inverse Zach transform, okay. And if you take this expression from the previous slide and you put it in here, you can actually simplify this double integral and it is actually this thing. So, this is called the inverse Zach transform, okay. An inverse Zach transform obviously is defined only for delay Doppler functions which are quasi periodic. because only quasi-periodic functions can have a time domain representation, right. Because you take any time domain signal, its Zach transform has to be quasi-periodic, that is why. Okay. That is the only new thing that you get here. Otherwise, conceptually it is the same as your Fourier transform, right. You will see in this paper and also in this book, there is a lot of discussion about this basis and these things. And this is what I was telling you. I mean this everybody knows, right. I mean when you do OFDM, your basis is basically sinusoids. I mean they are sinusoids in time, but actually in the frequency they are Dirac deltas or pulses in the frequency domain. And what you actually do is your information signal in case of OFDM is in the frequency domain on the subcarriers, right. And then you do a inverse Fourier transform, you get the time domain realization, and that is what is actually transmitted over the channel. At the receiver you receive a time domain signal, and then what do? You take its Fourier transform, you go back to the frequency domain, right. And then on this received frequency domain signal you do all your demodulation, channel estimation, almost everything, right. So we just have to take that philosophy here, as simple as that. The same thing will carry over, right. Now your carrier waveform is pulse-on, this one, right. Tell me, I mean the carrier waveforms in case of sinusoids are sinusoids in case of OFDM, right. And what is the representation of sinusoids in the frequency domain? It is a narrow pulse, it is a Dirac delta, right. Similarly, if I talk of the basis of pulsons, then what is the representation of a pulson in this basis of pulsons? It has to be again a Dirac delta, right. So this pulson tau naught nu naught in the delay-Doppler domain, it is basically a narrow pulse which is located at tau naught comma nu naught. It is exactly like having a sinusoid of frequency f0. If you take the Fourier transform of a sinusoid of frequency f0, then you will get a Dirac delta at f0. Similarly, if you have a pulson tau naught nu naught and you take its Zach transform, you will get a Dirac delta pulse at tau naught nu naught, conceptually the same. But of course, this pulse will actually repeat because it has to be a quasi-periodic function. So it has to be, if it is at tau p, it has to be also there at tau 0 plus tau p, also at nu 0 plus nu p. So it will be there infinitely. But if you look at one box in the delay-Doppler domain, so let us say you have this box which is tau p along the delay domain, along the Doppler it is nu p, then within this box you will see only one pulse. That is what I mean when I say it is quasi-localized, okay. So it is kind of localized but not really localized, okay. And this is how I am going to communicate. I will send information QAM symbols on these pulses and different QAM symbols on different pulses located at different tau naught nu naught, okay. So you could have another pulse over here at tau 1 nu 1, right, and at tau 2 nu 2, right, and then you multiply each one of them with a different QAM symbol, add all of them up, and that is your information signal here, right. Some of them will actually be pilots. You take the inverse Zach, you get the time domain, that is what you transmit. This goes over this doubly spread channel whose delay-Doppler spreading function is h tau nu. You receive this time domain signal y t at the receiver. You again you take its Zach transform and you go to the delay-Doppler domain, okay. So this is the delay-Doppler representation of this received time domain signal. It turns out that obviously this ydd has to be related to this xdd. For example, as I said, when you have a delay only channel and you are sending sinusoids, then what you receive on a subcarrier is what you transmitted on the subcarrier multiplied with the gain of that subcarrier. Here, or for that matter, if you have an LTI channel and you are transmitting in time domain, then what you receive is given by the convolution of the transmitted signal with the channel impulse response, right? You have a linear convolution happening there, right? So, here also you have something like that, but it is not linear convolution. The output in the delay Doppler domain is given by the twisted convolution of the input with delay Doppler spreading function of the channel. This is the big result, okay? And it's proven in the book, it's there in my papers. So basically, yeah.
Question.
Yeah.
So the DD domain representation is quasi-periodic, right?
Yeah.
In practice, but in real system implementation, we just consider one.
Yeah, so you just consider one box. So because you design everything for one box, and at the back of the mind you know that it is just going to repeat quasi-periodically, okay? Right? So it's just a mathematical construct, and but I'll show you how. I mean this pulse-on is actually not limited in time and bandwidth, if you see. But I'll show you how to limit it in time and bandwidth, and you have to basically do some filtering in the delay Doppler domain, and that will ensure that the signal that you are transmitting, I mean infinitely it's a pulse-on, but you can limit it in time and bandwidth actually. But still it's delay Doppler representation, even though it is limited in finite time and bandwidth, the delay Doppler representation will still be quasi-periodic and everywhere. I mean that's the definition, I mean that's the whole mathematical framework, right. See, this already is giving you a hint that if you can somehow estimate this guy, then you are predictable, right. So this is my pulse-on at tau naught nu naught, okay, and if I take the Zach transform of this thing, okay, which I have written here, you take, so this is the Zach transform of this pulse-on, then this signal that you get is the delay Doppler representation of that pulse-on at tau naught nu naught, right, this thing, and this is actually the mathematical expression. I mean if you see here, if you put n equal to 0 and m equal to 0, then you will get a Dirac delta at tau naught nu naught, right, and then corresponding to different n and m you will get the other copies of this Dirac delta, right. And if you see, the shifts are always with integer multiple of tau p along delay and integer multiple of nu p along Doppler. So in a way, so the quasi-periodicity is here, it is there inside it, okay. And if you want to check, I did some math just to show that if you take this mathematical expression and you apply the inverse Zach transform, which is this equation, okay, then if you go through, you will get back your time domain realization, which is here, this one, okay. Just for you to be satisfied that this is indeed the delay Doppler representation of this signal, okay. You wanted to ask some question? Yeah, no, okay. Is it okay so far? Okay, at least conceptually. I mean, to really understand it, you will have to work it out with pen and paper, and the book is there to help you. Okay. So this is the delay Doppler representation of the pulse, the pulse-on at tau naught, tau 0, nu 0, right. But I can actually write it as the standard pulse-on at 0, 0, the standard pulse train, which is, so this is, if you put tau 0 equal to 0 and nu 0 equal to 0, then you will get basically the delay Doppler representation of the standard pulse-on, the standard your pulse train that we studied in the sampling chapter, right. So it turns out that this pulson at the delay-Doppler representation of a pulson at tau 0 nu 0 is simply the, you take the delay-Doppler representation of the standard pulson at 0 0 and you do a twisted convolution with this shift operator. So, this is the shift operator. So, this is going to shift, if you see you have tau minus tau naught and nu minus nu naught. So, when you do a twisted convolution with the shift operator, so this is how you can generate, starting with the standard pulson at the origin, you can generate any other pulson using the appropriate shift. Okay. And here I have explicitly done this because this twisted convolution is basically a double integral, right. So, I have shown all the steps of the twisted convolution and how you reach here. Okay. This is just verification of this thing. Okay. I mean, this is how, I mean, this is one box here, but as you can see, they are repeating quasi periodically throughout the entire delay-Doppler domain, right. I mean, one question which will come to your mind is, what is the frequency or what is the Fourier transform of a pulson, right. So, you have this pulson at tau 0 nu 0, what is the Fourier transform? As I said, I mean, now this proof is very simple to see. If you start with your pulson, this one at tau 0 nu 0, you can actually write it like this. You take the standard pulse train, you first give it a frequency shift of nu naught and then you delay it. This is linear convolution, the star is linear convolution. You delay by tau naught, right. Okay. That is how you will get this, it is very easy to check. Okay. Now, I have to take the Fourier transform of this thing, right. That is equal to the Fourier transform of this multiplied, because your linear convolution becomes multiplication in the frequency, right. So, we have to, so what is the Fourier transform of this? It is written here, I mean this part, right. I mean the Fourier transform of this is simply the Fourier transform of the standard pulson shifted in frequency by nu naught, because this is a frequency shift operator, which is this thing, right. And then because of this convolution, you will have a multiplication with the Fourier transform of this term. The Fourier transform of this term is only this also you know, right. So, therefore, it turns out that the Fourier transform of the pulson at tau naught nu naught is simply you take the Fourier transform of the standard pulson at the origin and first you shift it by nu naught and then you have this phase factor. Okay. Now, for the, I mean this I had written, I mean for the pulson at the origin, this is the Fourier transform. It's I mean this we already know from the sampling chapter, right. So, you just take this and this thing and you shift it by nu naught and multiply with this, you get this final expression. Okay. Now, if you see this also in the frequency domain, what you actually have is, and this is like a tone in the frequency domain, okay, and this is a pulse train in the frequency domain, where the Dirac deltas in the frequency domain are located at nu 0 plus nu p, nu 0 plus 2 nu p, and like that, nu 0 minus nu p, like that, right. It is a pulse train. So, the pulson is also a pulse train in the frequency domain, that is the key thing that I am saying. Basically, a pulse train multiplied with a tone. So, it is a pulson. Okay. I will quickly go over some properties of Zach transform. Okay. So, this is the very first property, the most important one, that the output is given by the twisted convolution of the input with the delay-Doppler spreading function of the channel. And so, this is in the book in appendix 2.c, chapter 2 of the book. Okay. And this is your the expression for twisted convolution. It is like a linear convolution in 2 dimension except this term. Okay. Very interesting thing. You would have you know this result, right. in the frequency domain, I think it's called the generalized Parseval's theorem. If you take the inner product in time domain, this is the inner product between two signals in time domain, right? Then inner products are preserved in the frequency domain also, right? I mean, you know that this is equal to the integral of xf times the complex conjugate of yf df, right? And that is true here also. So, here also the inner products are preserved. Of course, here because you have a quasi-periodic signal, you only integrate within that box. And a special case of this result is if you take yt to be equal to xt, you see that the energy in the time domain and in delay-Doppler domain is also preserved. Okay. Actually, I mean, this is a unitary transformation. Basically, this, just like Fourier transform is a unitary transformation, it preserves the inner products. Zag transformation is also unitary, it preserves the inner products. We already seen the inverse, I mean the inverse Zag transform that we saw was taking you from the DD representation to the time domain representation, right? That is the inverse Zag transform, right, which is given by this formula. But there is another inverse Zag transform which takes you from the delay-Doppler representation to the frequency domain representation, and we call it the inverse frequency Zag transform, right? And that has this expression, because from the DD domain you can go to the time, you can go to the frequency, right? But of course, I mean these transforms are only defined if your function xdd is quasi-periodic, right. So, these are also discussed in an appendix in the book. This is a very nice picture. It actually shows that your Fourier transform is a composition of these Zag transforms. They are related, right, because let us say that, so what is the Fourier transform in red? You start with a time domain representation and the Fourier transform takes you, look at the arrow, from time to frequency domain representation, right. But instead of going it like this, we can also go, we can start with the time domain representation, we will first go to the delay-Doppler representation by taking the Zag transform. So, you start with your xt, you take Zag transform, the time Zag transform. So, the time Zag transform zt will take you from time to delay-Doppler representation, and then from delay-Doppler you can go to the frequency by using the inverse frequency Zag transform, and you get the frequency domain representation, right. So, basically your Fourier transform is a composition of the time Zag transform and the inverse frequency Zag transform. Okay. We have this triangle. We will try to see some properties of twisted convolution. I will take some examples there, okay. And so, any kind of filtering that you have to do in the delay, see the filtering that you do in time domain is always linear convolution, right. At the transmitter you do this what is called pulse shaping, at the receiver you do matched filtering, right, but they are all linear convolutions mathematically, right. Here also at the transmitter I have to do pulse shaping, at the receiver I will have to do match filtering, but here it is not linear, it is twisted convolution. And there is a reason why we do twisted convolution, I will come to that. Okay. It is very simple, if you do twisted convolution as the filtering operations at transmitter and receiver, the channel is anyways acting through twisted convolution. So, the net input output relation is going to be a cascade of twisted convolutions, which is itself a twisted convolution. We discussed that cascade of channels, right. So, you have to think of your match filtering and your pulse shaping also as a kind of a channel, right. So, it becomes a cascade and that can be modeled as a single twisted convolution. Instead of that, if you let us say the channel will always do twisted convolution, I mean that is what it does, right. If you have a doubly spread channel, it acts through twisted convolution, we saw that, right. At the transmitter and receiver, if you do your filtering in the delay-Doppler domain which is not twisted convolution, something else, then the cascade cannot be written as a system as a single twisted convolution, and then it is quite possible that your input output relation may not be predictable. because it will be something else, right. The first thing is that the twisted convolution is not commutative, unlike your linear convolution, and the reason is, I mean, it's a very simple example. Suppose I have two channels, okay. The first one, you take your input, you pass through the first channel only gives you Doppler shift, and then after that you have your, so you have first input, then Doppler shift, and then you have delay shift, you get something at the output. Instead of this order, if you reverse the order, you first do a delay shift and then a Doppler shift, the outputs will not be the same for the same input, because that's what I mean when I say that it's not commutative, okay. But the good thing is it is associative, okay. So it satisfies this property. Twisted convolution. Again, twisted convolution you can, the signals that you do twisted convolution, they need not be quasi-periodic. They can be any functions in the delay-Doppler domain. For example, h tau nu is just a function, delay-Doppler function, right. It's not quasi-periodic, okay. But we have this result that if you have a quasi-periodic signal like ADD, which is basically the delay-Doppler representation of some time domain signal, and if you do twisted convolution with some function g tau nu, where g tau nu is just any arbitrary delay-Doppler function, it need not be quasi-periodic, the output will always be quasi-periodic, right. So that is the result, okay. And it makes sense, right. So your YDD was h tau nu twisted convolved with XDD. H tau nu is not quasi-periodic, but XDD is, right. If you go back here, over here, this is quasi-periodic, this is not, but then because of that, the fact that twisted convolution preserves quasi-periodicity, YDD will be quasi-periodic, okay. Now this is an example of how I will do filtering, okay, but it's an example, and at the same time it's also going to kind of fill in one of the building blocks of Zach OTFS modulation. So I am trying to do two things at the same time, okay. So why do we do transmit pulse shaping? Because I cannot simply use this as my carrier waveform. Why? Because it has infinite time duration, and if you look at the frequency Fourier transform of this thing, it's also a pulse train, so it's infinite bandwidth, right. So I cannot, that's not a practical signal, right, for communication. So how do you limit it in time and bandwidth? Very easy. You take your pulson, you first do a linear convolution with, so you limit the bandwidth. So for example, your W1 could be a sink. So W1 could be something like this. So this will limit the bandwidth to the interval minus b by 2 to plus b by 2, right. And after that you multiply with a time window, Wt, capital Wt. So capital Wt could be the rectangular window in minus t by 2 to plus t by 2. So when you do that, so you do the math, you basically get this, okay. Now this is also a pulson, okay. I call it a physical pulson, physical because it has finite time and bandwidth, okay. So it's limited to the time interval minus t by 2 to plus t by 2, and it is approximately limited to the bandwidth minus b by 2 to plus b by 2, right. And if you see here, you have pulses here, right, W1, these are the pulses, and you have a pulse train in a way, right. But if you see each of these pulses W1, see what is the spread of W1? Roughly 1 over b seconds, right. So each of these pulses is roughly 1 over b seconds, okay. And then this term here is just going to limit, it is like a window, everything outside minus t by 2 to plus t by 2 will just become 0, okay. So this is my physical pulson. Of course the physical pulson depends on this W1 and W2, right. You choose a different W1, W2, you get another physical pulse on. It turns out that I can actually write this operation like this. So, let us say small W2 is the Fourier transform of capital W2. Then this capital W2 can be written as the inverse Fourier transform of small W2, right. Instead of f I am using nu, but it is just a mathematical variable, does not matter. So, this is this one, and then you multiply that with this term. Now, this term is simple linear convolution in time. So, I have written it like this. Okay. Okay. This is just your convolution, linear convolution of W1n. This is your Dirac delta pulson at tau naught nu naught. Okay. And then I combine these two integrals as a single integral. Okay. Okay. So, you get this equation, right. And this, now this function depends only on tau and nu. So, I am abbreviating it as W subscript Tx, tau nu. Okay. Now, I want to know what is the relation between the delay Doppler, what is the delay Doppler representation of this after you do this pulse shaping. Basically, you did the filtering followed by time windowing, you got this physical pulson. What is the delay Doppler representation of this physical pulson? That is the question, right, that will come to mind, and it is not very difficult to see that. If you remember this equation, right, this is when I have a signal xt which I am transmitting, it is passing through a doubly spread channel whose delay Doppler spreading function is h tau nu, and this is my received signal, right. And when I took the Zag transform of the received signal, this is the result that we have seen, right, that the Zag transform of the received signal is simply the twisted convolution of h tau nu with the Zag transform of the transmitted signal, right. Now, you compare this integral with this integral here. I mean this integral and this integral, they will look very similar. I mean, look at this term here also, right. Instead of x you have p of tau naught nu naught, instead of h you have this wtx, this thing. So, now once you know this result, you can easily tell what will be the, so what will be the Zag transform of this physical pulson, which I am denoting with this thing, with this variable, is basically the physical pulson, but I have to write this wtx because the expression of this will depend on wtx, right. So, the Zag transform of this receive, you have to think of this like a received signal, you have to think all of this as the channel action, where you are first doing a filtering with the sinc filter followed by time windowing. Think of that like a channel action. So, it is a channel action, it is a channel whose delay Doppler spreading function is actually wtx, and therefore, the delay Doppler representation of this is this the delay Doppler spreading function of the channel action, which is h tau nu, now here it becomes wtx, twisted convolve here and here with the delay Doppler representation of the input, which was your Dirac delta pulson in this case, right. So, this is what you get. I mean the delay Doppler representation of the physical pulson after a filtering and time windowing is nothing but your Dirac delta pulson, delay Doppler representation of that, which is actually a Dirac delta, quasi periodic Dirac deltas at tau naught nu naught and then plus integer multiples of tau p and nu p, that twisted convolved with wtx. So, basically the pulse shaping is nothing but it is like a filtering operation in the delay Doppler domain, filtering using twisted convolution. That is what I was trying to explain. Okay. And then what will happen very interestingly is, if you see these, this has Dirac delta pulses at tau naught nu naught and with integer shifts of tau p nu p. when you do twisted convolution with this filter, now this WTX, look at the expression of WTX tau nu. It is a two-dimensional pulse, imagine it, right. What is going to be the spread of this thing along the delay domain, along tau? That will depend on this term. But W1 tau, the spread is 1 over bandwidth. For example, if you take W1 to be this thing, if you want to limit your signal to a bandwidth B, then this will have a spread of 1 over B. Similarly, because you want to limit your signal to a time duration of capital T, the spread of the Doppler spread is going to be 1 over capital T. So, this pulse here or function is localized in a region which is roughly 1 over bandwidth along delay and 1 over time along Doppler. Okay. And so, this will do, I mean the effect of this two-state convolution will be therefore to kind of smear that Dirac delta. I mean for example, in time domain if you take a Dirac delta and convolve with a pulse, then the output is no more a Dirac delta, it is basically a spread, right. So, this will do that spreading, but the spreading will only be to an extent of 1 over B along the delay and 1 over T along Doppler, right. So, that is the kind of delay Doppler representation of a physical pulse-on. It will still be quasi-periodic. Okay. So, that is what I have shown here, that I mean this was your Dirac delta pulse-on and you made a physical pulse-on out of it by doing this operation. First you do filtering with the sinc filter. Instead of sinc you could use some other filter also, but roughly this thing is required to limit your signal in bandwidth to a bandwidth of B hertz, and then you do a time windowing, right. But this entire operation can also be done in the delay Doppler domain. Basically you take your pulse-on Dirac delta, you take the Zag transform, you get this signal and then you do a two-state convolution with this filter. I call this as the filter because it is kind of spreading it, right. And then this is the I mean this is basically the delay Doppler representation of the physical pulse-on. So, if you take the inverse Zag transform of this thing like that, then you get the time domain representation of the physical pulse-on, which is this one. Okay. Is this clear? So, that is what I have written here. Pulse shaping smears the Dirac delta dd pulse over 1 over B along delay axis and 1 over T along the Doppler axis. Okay. And that is it. This is your
just on previous page, just for mathematical pages, if you switch the operation, the linear convolution,
you can do that. Yeah, then this term will go away. Yeah, but it will still be something like this. Yeah, very nice. Thank you. I am happy that I am getting very smart and intelligent questions, which means that I am able to communicate reliably with you, right. Good, very nice, very nice. Okay. This is now your physical pulse-on. It is still located at tau naught nu naught, but it got spread. It got spread by 1 over B along the delay and by 1 over T along the Doppler, but and it is still quasi-periodic. Okay. Those things do not change. And if you look at the time domain realization, it will only be limited to this duration of T seconds. Outside that it is not there. For example, if you use a strict rectangular window, then it is exactly not there. If you use some other windows, then there might be little energy outside. Depends on how you do the pulse shaping, right. And so you have these pulses now. Earlier these pulses were Dirac deltas. Now each of these pulses will have a narrow spread of 1 over B, B inverse, right. And the frequency of this tone will be nu naught, because this pulse-on is located at nu naught, right, nu naught tau naught. If you take the Fourier transform of this thing, then you get the frequency domain realization of the physical pulse-on, which will also be a pulse train, but now it will be limited to a bandwidth of B hertz, right. because of that filtering, right. And now each of these narrow pulses will be spread by 1 over t along Doppler. So, it is 1 over t, you see the width of each of these narrow pulses is 1 over t. And the location of the pulses are at nu 0 plus nu p, nu 0 plus 2 nu p, and like that, right. And it is also multiplied with a, this is like a mathematically a sinusoid in the frequency domain. Now, something very interesting. Now, look at this time domain realization of the physical pulson. Now, suppose, now my only constraint on tau p and nu p is that tau p into nu p has to be 1, because nu p is 1 over tau p. So, imagine this rectangular hyperbola tau p times nu p equal to 1. Okay. So, this you see this curve is a rectangular hyperbola, right, tau p into nu p equal to 1. As you choose different values of tau p nu p on this hyperbola, you get different Zach transforms, right. They are different bases of pulsons, right, because the period will change. Now, if I take tau p to infinity, if I go to this end like that there, right, if your tau p becomes infinity, then what will happen is only this pulse will remain. These other pulses on both this positive side and the negative side, they will go to plus infinity and minus infinity, and only one pulse will remain at tau 0. That is my time domain modulation using time domain pulses. That is a special limiting case of pulson. Similarly, if my nu p goes to infinity, then if I look at the frequency domain realization, if my nu p goes to infinity, then I will only have a single frequency domain pulse at nu naught, and all these other pulses will go to plus infinity or minus infinity in the frequency domain. I am left with only one pulse at f naught. That is my frequency division multiplexing, right, OFDM, right, subcarrier at f0. So, they are special cases of this more. So, Zach OTFS is a more generalized, kind of a, it is not just one modulation, because each point here on the hyperbola will give you a different modulation. It is like a family of modulations, with the extremes being your FDM and TDM. Now, this question people ask me, so that is why I included this slide, is I have now that you know this pulse shaping, I have shown it here. Okay. So, you start with your, this is the Dirac delta pulson, the DD representation at the transmitter. You do a pulse shaping, which is just twisted convolution of this with the pulse shaping filter. Okay. This is the output in the DD domain, which is, this is the physical pulson basically. Okay. And then you just take the inverse Zach transform of the physical pulson, that will give you the time domain realization of the physical pulson. That is what is transmitted over the channel. You receive that, you receive the channel output in time domain, you take the Zach transform, you get the delay-Doppler representation of the received signal here. And what do we typically do at the receiver in normal communication? We do a match filtering. And what is match filtering here? Match filtering is the same type of thing. You limit the signal received in bandwidth and in time, right? And that also can be implemented as a two-state convolution with some other filter, WRX. And then the output of that is what? Right? I am denoting it with YDD WRX. Okay. So, this is my output in the continuous delay Doppler domain. This is my input in the continuous delay Doppler domain. There has to be a relation between them. So, what is that relation? It is not very difficult. So, let us start with the output here. The output here is a two-state convolution of WRX, okay, with the Zach transform of the received signal, right. But this we already know that the Zach transform of the received signal is simply the delay Doppler spreading function of the channel two-state convolved with the DD representation of the input, which is actually this physical pulson, right. So, you get the first, so this thing inside the bracket is basically going to be the delay-Doppler representation of this received time domain signal, right. Next, what is, now we also know that this physical pulse-on in the DD domain is equal to a two-state convolution of the pulse shaping filter WTX with the Dirac delta pulse-on. That is what I have written here. So, you have a square bracket and then inside for this thing I have written it as a two-state convolution of WTX with this is my Dirac delta pulse-on, right. And now, if you see I have a cascade of two-state convolutions, because the two-state convolution operator is associative. So, what I can do is I can take all of these filters and I put it together as one filter. I mean WRX two-state convolve with the channel two-state convolve with the transmit pulse shaping as an equivalent channel H effective tau nu. And so, the input output relation is that the output here after the match filter is simply a two-state convolution between the input, the Dirac delta pulse-on input, two-state convolve with the effective, now this models the effective channel filter, right. I call it the effective channel filter in the DD domain, of course, right. And see, it is not very different from what we do when we have LTI channel and you are communicating, using time domain pulses, for example. Then you do pulse shaping at the transmitter, which is just linear convolution with a pulse shaping filter, followed by the channel will do its own linear convolution, and then at the receiver you do linear convolution or filtering with a match filter, and the output of that is your final output in the receiver, the match filter output. Now, the match filter output therefore is simply equal to the initial input signal linearly convolved with the cascade of the transmitter pulse shaping, the channel and the receive match filter. That is what I am doing here, it is the same thing conceptually, there is nothing different here. Okay. And so, now you can very well see that, I mean this kind of a input output relation is predictable if I exactly know this H effective tau comma nu, or I should be able to somehow estimate it accurately. If I can estimate H effective tau comma nu, then my waveform is predictable because I can accurately predict the output of the channel for any arbitrary input. Okay. But the question is, how do we do that, and is that always possible, or are there any conditions under which we can acquire this H effective tau nu under certain conditions?
So, if you are using ideal pulsons, then for channel estimation purpose, you can perfectly reconstruct the channel in the DD domain, right? But now, because you are considering the practical situation, so you include the pulse shaping, and in that case, your impulse in the DD domain will spread. And in that case, you will lose some resolution of channel estimation. So you are going to find some condition under which you can have
no, I mean see, I am not really interested in H tau nu.
Yes.
Because for me what just matters is this thing, H effective tau nu. Okay.
But you still need to
you estimate H effective. Yeah, I'll show that. You don't really need to. That is when I will go to the discrete delay-Doppler domain.
Okay.
So, I mean that is what we do in the time domain, right? You start with discrete time input symbols x n, and you mount that on an impulse train, and then you do a pulse shaping of that, right. Something similar I will do. I will define a discrete delay-Doppler domain. I will have my information symbols in the discrete delay-Doppler domain. I will convert that to a continuous DD signal and then do this pulse shaping and something like that. Okay. But your question is very much correct. See, so far this is all mathematical, it has nothing to do with practicality. Okay, this has to be converted into a practical system, which is another session. Okay, but in this session I am just showing you what's the real math behind it, and then we'll later see how to convert this into a practical system. Okay. Okay, I wanted to discuss why the input output relation, if you use pulsons, then the input output relation is predictable. Okay, why is that so? Okay. Now suppose, I mean, this first equation, now we know it, right, that this is your Dirac delta pulson at tau 0 nu 0, and the received signal is basically this two-state convolved with the effective channel, right. And then if I take this thing, now this expression I know is equal to this, right, this is there in a previous slide, right. This is the delay-Doppler representation of the Dirac delta pulson at tau 0 nu 0. And now you do a mathematical, I mean, two-state convolution is a linear operator, so you can actually you can take the summation outside. And so when you can do a two-state convolution of H effective with each one of these terms separately, with the n comma mth term, this is what you will get, two-state convolution. And if you really see this, it's very interesting. I mean, what you are actually seeing is, if you take any particular n comma m, okay, it's nothing but you have your H effective tau nu, and you are just shifting it by tau 0 plus n tau p along delay, and you are shifting along Doppler by nu 0 plus m nu p. You see this minus and minus here, right. So it's basically now I got copies of H effective tau nu shifted by these numbers, right, something like this basically. So I mean, this red dot is basically the Dirac delta pulson. Now I am showing, now here my x axis is the delay axis, y axis is the Doppler axis. And now this I have shown for the special case where my channel is ideal. So there is no delay spread, there is no Doppler spread, AWGN kind of a channel. Now for that case, what will happen is that your Dirac delta is the red dots, of course it is quasi periodic, and then when you do the spreading, and when you do the match filtering and the transmitter, you do basically your pulse shaping, there is a spread, right. So you get spread. So now this pink colored circle is what is showing you that basically denotes this thing H effective two-state convolved with the Dirac delta pulson. So basically what you are receiving if you have an basically ideal channel. Okay, I mean, this is the physical channel. Of course, the effective channel is you have to do a two-state convolution with the pulse shaping and the match filtering, right. And that is because of that only there is this spread comes. So that is why the pink circle is bigger than the red dot, but it is still quasi periodic. Now suppose now I do not have an AWGN channel, I have a single path wireless channel. This is the physical channel where that single path is giving me a delay shift of tau 1, it is giving me a Doppler shift of nu 1. So again what will happen is, now what you will receive, it will still look very much like the pink in terms of the spread will still be the same, 1 over b and 1 over t, but you see the pink ellipse has now shifted from the red dot. And what is this amount of shift? The amount of shift is exactly equal to tau 1 nu 1. So the effect of the channel basically is, see, because of the pulse shaping you get that spread. So you go from the red dot to the pink dot and the channel shifts you, right, by amount equal to tau 1 along the delay and nu 1 along the Doppler. That's how you should visualize it in your mind. Okay. So these pink ellipses They together form your received signal for the single path channel case. But in a real channel you will not have a single path, right? You will have multiple paths. Now I go back to my example channel which I started with, where you have you have brown, green, yellow and blue, right? So when you transmit your red dot from here, I mean, well, what you actually transmit is not the red dot, but I mean your information is there in the red dot, right? And it's basically a pulse on, Dirac delta pulse on at tau naught nu naught. Now at the receiver you will receive a blue ellipse, which is basically because of the reflection from the first reflector, right? Now if you see, that is slightly shifted to the right, because if there was no delay, then it should be the center of the red and the pink ellipse, pink dot, and the pink circle and the red dot should have the same center. But now it's not the case. If you see the brown one here is slightly shifted to the right because of the delay. This reflector 1 is giving you some delay, and the reflector 2 is also giving you the same delay. I mean, if you look at the shift along the x axis is the same, but along with the delay, the blue one is also giving you a Doppler shift, and that is why the blue is slightly on the positive side. The center of the blue circle is up because of that Doppler shift nu 2. And similarly you can plot the circles that you receive because of reflector 3. Again, for reflector 3 there is no Doppler shift. So the center of the red dot, the center of the brown and the green dot, I mean circles, is along the same horizontal axis, because there is no Doppler, there is only delay shift, right? And then the yellow gets a negative shift along the y axis because it's going, this van is traveling in the opposite direction compared to this car. It's a negative Doppler. Okay? So it comes, so that yellow comes down. And of course this thing will repeat quasi periodically. I have not shown the entire infinite repetition, I have just shown 4 copies. Each circle is 1 over b, 1 over t, roughly order of that. Yeah, 1 over b, 1 over t. The red dot is really a dot, but I wanted to show it, so that's why I have shown it a little big. It's actually a complete dot, okay? But if I just give a dot, you will not be able to see, that's why. So now for the receiver, what matters is, I mean all these blue, yellow and all this will start overlapping, right? So you cannot separate them individually, that's not possible. Okay? So what matters to the receiver is just the union of all those circles that you get from the different reflectors, right? And I have, if you see, there is a spread in the delay, right? So the delay spread is the left to the right along the delay, how much is the spread of whatever you have received, and that spread is tau s. I am going to denote it with tau s. Okay. Similarly, the spread along the Doppler I am going to denote with nu s. Okay. So that is my delay and Doppler spread. And then coming back to this question of how do I estimate this h effective tau comma nu, at least conceptually. How do I estimate that h effective? Because if I estimate that, then I am done, then I am predictable, right? My thing is that as long as this tau s, now remember all these copies, they are separated along the x axis by tau p, that is the delay period, and along the Doppler the separation is by, from here to here is how much? Nu p, and from here to here is tau p, right? Now if my delay spread of the channel tau s is less than tau p, and the Doppler spread nu s is less than nu p, then all these will not, I mean for example, right, the way that I have drawn here, none of these are overlapping, right? I mean the yellow circle here is not overlapping with the blue or any other circle here, right? This thing is just separate from the other ones. And in fact, each one of them together is like one of the terms in the summation here. Example, n equal to 0, m equal to 0 corresponds to the summation, that term corresponds to, let us say, this one. N equal to 1 and M equal to 0 corresponds to this received response. So, if I satisfy that condition, that the delay and Doppler spread of the channel are less than the delay and Doppler period, which I call as the crystallization condition. If that, so I mean, it is up to you. You can choose your delay Doppler period very smartly so that that condition is satisfied, right. And as long as that is satisfied, all these copies, here I have only shown 4 copies, will be not overlapping with each other, they will not overlap. And so, when they do not overlap, in fact, when you put n equal to 0, m equal to 0, you get the first term is this itself. I mean, this is when, suppose I transmit as a pilot the standard pulse on at the origin 0 0. So, tau naught is 0, mu naught is 0, and then when you write the summation, it becomes this basically, with tau naught 0, nu naught 0, and then if I take the first term here, it is nothing but H effective itself, right. So, whatever, if I satisfy that crystallization condition, then what I am going to receive in this n equal to 0, m equal to 0 box is basically going to be H effective itself. And that is conceptually how you will estimate H effective. That is it. You just send your pulse train, of course the physical pulse train, you do the pulse shaping and all that, and then you send it, and then you receive it, you take the Zark transform, and that is it. Just look at one of the boxes. As long as you are satisfying the crystallization condition, you can just estimate it very easily. So, this is now all those green, yellow, brown circles, I have put it into a pink ellipse. So, this pink ellipse is like the union of all those smaller circles, right, because in general you may not have 4 paths, typically you will have 10, 12, 15 paths, right. So, the union of all that is this pink ellipse. Of course, you will get quasi periodicity, right, that is why you have not just one ellipse, you will have infinitely many pink ellipses. And the spread of such a pink ellipse along the Doppler axis is nu s, along the delay it is tau s. Okay. Now, this is a good case, this is the, I call it the no aliasing case or the no overlapping case. Here what is happening is these 4 pink ellipses, in general infinite pink ellipses, are not overlapping with each other because you are satisfying this. So, this is the crystallization condition. So, if you satisfy this condition, then there is no overlapping, I call it as no aliasing case, and that is what I want to be like. But if you did not choose your delay Doppler period appropriately, suppose here what I have shown is if your delay spread is very large, if it is even larger than your delay period, then you will start to see overlap along the delay domain. Along the delay domain, these ellipses will start to overlap, and I call that as delay domain aliasing. Okay. Same thing can happen along Doppler. If your Doppler spread is very large, it is larger than your Doppler period, then you start to alias along the Doppler axis. In either of these aliasing cases, you cannot estimate H effective because of this overlapping and aliasing, right. So, that is why, so basically your input output relation is, when you use pulsons for communication, the input output relation is predictable as long as you satisfy the crystallization condition, right. I have drawn the hyperbola here, right. The right extreme is time domain modulation, left extreme is frequency domain, we saw that. In between you will have no aliasing, that is the crystalline regime. If you go too much to the right, what you will see is that your tau p is going to infinity, which means that your nu p is becoming smaller, and so you will start to see aliasing along the Doppler domain. And because of that you get selectivity in along the delay, which means that now here what these heat maps are basically, so I have a 4 by 4 case, okay. So, I am transmitting 16 pulsons. When you are in when you satisfy that crystallization condition, then the received energy is the same irrespective of whichever pulson you transmit. it's like, it's like saying that you have, in an AWGN channel, right, irrespective of the time when you transmit your time domain pulse, the received energy is same, right. But the moment you have Doppler, then the received energy can, or you are fading, then the received energy will fade in time, right, when you have Doppler, for example. But here what will happen is, as long as you satisfy the crystallization condition, you will not have fading in the delay Doppler domain. So, the energy on all the on all the pulsons is similar, it's almost the same. And that is where this name of crystallization came about, because it looks like the surface of, you have solids which are crystalline solids. So, when we plotted this heat map, it looked like that. So, that is why we given this name of this condition to be crystallization condition. Okay. Of course, when you are not, if you go to this extreme, you have Doppler domain aliasing, you go to this extreme, you have delay domain aliasing. And when you have this aliasing, then the received energy is not the same for each pulson. The received energy will vary depending on which pulson you transmitted at what location. And I call it as fading in the delay Doppler domain. For this session, this was I think I finished it much before time. About time, okay, good. So basically what we did in the last two sessions was that in the first session I showed that time frequency signaling or using in doubly spread channels is not predictable, right. And then we got this idea of pulsons, right, using pulsons for communication. And we defined the basis of pulsons, we defined the Zag transform, and then we also showed that the pulsons, the way they interact with doubly spread channels is through twisted convolution, right. And we have this notion of effective channel, right. We showed that effective channel can be acquired, and if you can acquire it reliably, then you have a predictable input output relation. But for that, the crystallization condition should be satisfied, right. Now, the next thing we will do after lunch is, but what I have shown is not a practical implementation, because this is all continuous delay Doppler domain. I will talk about discrete delay Doppler domain, and I will also discuss about some comparisons with CPU OFDM. Okay. But even before that, I have to first define what is Zag OTFS modulation basically.